Hello everyone, I am Manwani, a fourth year student at IIT Guwahati. You might know me by my handles NM, by which I go on CodeChef and Codeforces. And today we are going to look at the problem characteristic polynomial verification and understand its solution. If you are worrying about the prerequisites required for this editorial, there are none. You do have to know Frival's algorithm to solve this question, but I'm going to explain Frival's algorithm in this session as well, so you do not have to worry about knowing something before this session. So now let us look at this problem. Given an array C of m integers and a square matrix A of dimensions n by m, verify whether the following equation is true. So we have to verify whether this equation given here is true or not. Where 0n is a square null matrix and in is the identity matrix, both having dimensions n by n. So we just have to verify whether C0 into in plus C1 into A, here C0, C1, C2 are constants, and A is a n by n matrix, A square multiplied by C2 up until Cm minus 1 into Am minus 1 is congruent to 0n or not, modulo 9n8 244 353. What does it mean by these two matrices being congruent? Two matrices A and B with each individual integer entries are said to be congruent modulo m if all entries of A minus B are divisible by m. This is denoted by A congruent to B modulo m. And the second note here, since our input output is large, prefer using fast input output methods. So this is a pretty straightforward question where you just have to evaluate whether this whole matrix is going to be congruent to 0 or not. Basically, you have to evaluate this matrix and check whether it is 0 or not. In input, we are given the matrix, the vector C and the matrix A in each test case. And the number of test cases here are 200, but as it is given that the sum of n over all test cases does not exceed 2000, we do not have to factor in the number of test cases in our time analysis. We just have to factor in the maximum value of n, which we can take as 2000. So coming on to the solutions that you can come up for this problem. First of all, you have the naive solution. In the naive solution, you would have to compute the whole left matrix. Let's call that matrix P. This matrix would be C0 into in. Multiplying C0 with the identity matrix would just take big of n time or big of n square times. So that is not that hard. Plus C1 into A, that is also going to take big of n square time. Plus C2 into A square. This is where the problems starts to arise. Because to evaluate A square, you have to multiply A with A itself, and the matrix multiplication time in the naive method is big of n cube, which is not going to fit in our time complexity, right? Furthermore, for the remaining terms as well, you are going to have a similar time complexity because there will be matrix multiplication there as well, and each matrix multiplication is going to take big of n cube time, right? Up until Cm minus 1 into a to the power m minus 1. It is given in the problem that m is small, m is less than or equal to 10 in the constraint, so we do not have to worry about the number of matrix multiplications as per se. The total number of matrix multiplication is going to be less than m square or around 100, so that is not a big value. But the main problem here is the time complexity it takes to multiply two matrices, which is going to be big of n cube. Which for n around 2000, it's going to be really large and not going to fit in the time complexity. Even if you're trying to optimize this approach by evaluating P and checking whether it is equal to 0n or not, if you're trying to optimize this approach by optimizing on the matrix multiplication time by using some advanced algorithms like divide and conquer, or there is much research going on matrix multiplication right now as well. You might use some algorithm from that research. You might be able to bring this complexity down, but you cannot bring it down too big of n square. Whatever time complexity you have is going to be greater than n square, or if you use a standard divide and conquer algorithm, then that algorithm would be then that time complexity would be big O of n to the power 2.78, which is not going to work. So the trick here is to use Frival's algorithm, and the Frival's algorithm is almost similar to what we are doing in this question. It's actually pretty identical. In Frival's algorithm, for the original Frival's algorithm, we had to check whether some product of two matrices A and B is equal to some other matrix C or not. We just have to check this point, right? And to check this point, we make a polynomial P, which is equal to A into B minus C, and we multiply this polynomial P by a random vector, let's say V, right? If this matrix is of size n by n, then of course this random vector that we have made should be of size n by 1. Multiplying this n by n matrix with a n by 1 vector, we would get another vector of size n by 1. Let's call that the resultant vector, which is of size n by 1. If this whole vector is constituted of only zeros, then the P matrix is probably 0, right? We say the P matrix is probably 0. If there exists at least one non-zero element in this resultant vector, right? If say this 0 is some non-zero element, let's say 5, and all of the rest are zeros, then we can say for certain that the P matrix was not 0 to begin with, because if A into B minus C was anything other than a 0 matrix, and if we multiply it with a vector and get if we multiply it with a vector, we can get a 0 vector or a non-zero vector. But if we had a 0 vector initially, then multiplying with another n by 1 vector, we would always get a 0 vector, right? So that is why if this whole resultant vector turns out to be 0, we can say P is a 0 matrix probably, and this is called the Frival's algorithm. We can of course change this Frival's algorithm by instead of multiplying n by 1 matrix on the right hand side, we can multiply 1 by n vector on the left hand side and multiply it with whatever P we had before, right? Whatever this P is, we can use this P here as well, right? And then just check whether this vector, whatever resultant vector we get of size 1 by n, whether this is 0 or not, right? The time complexity that this would take is big O of n square, and this is how. If we try to multiply V, which is a vector of size 1 by n, by our whole equation left hand side, which is P, the P matrix, which I can write as C naught I n plus C1 a plus C2 a square, etc. up until Cm minus 1 a to the power m minus 1. We can just take this V vector inside and multiply it with each of the terms independently. So C naught into V 1 by n into In plus C1 into V into A plus C2, and the way we avoid multiplying matrices in this A square term is by this. We first multiply the vector with A, right? This is going to take big O of n square time. Multiplying a 1 by n vector by n by n matrix is going to take n square time. And once we get that 1 by n vector, we multiply that vector with A as well, right? This is also going to take big O of n square time. So in a sense, each matrix multiplication now is taking big O of n square time instead of big O of n cube time. You can compute the rest of the terms similarly. Computing the third term, which is the C3 term, that can be done by V into A multiplied by A multiplied by A, and that whole multiplied by C3, and just adding these values up, you will get a resultant vector. And if that resultant vector is 0, then we will say that P is probably 0. And if that resultant vector is not equal to 0, then we can say for surely that our initial P matrix was not 0. Now the only thing remaining here is to verify what is the probability by which we can have a false negative, right? So there can be two cases, that the original P matrix was 0 and the original P matrix was not equal to 0, right? If the original P matrix was 0, then we would always get the resultant vector as 0 as well, right? There is no case that the resultant vector will not be equal to 0 if the original P matrix was 0. But if the original P matrix was not equal to 0, then we can get resultant equal to 0, and we can get that resultant is not equal to 0. right? This case and this case are correct, right? These are the cases in which our algorithm does not fail. But if we get on this case, then our algorithm has then our algorithm will fail, because if the resultant vector is 0, then we are declaring that our original matrix was 0 as well, right? So we are declaring that p was 0 even if p was not equal to 0 initially, right? So we just have to find out what is the probability that we can get in a case like this when p is not equal to 0. And to verify that probability, we are going to do some probability analysis. Let's imagine the initial p matrix like this. As we say that the p matrix is not equal to 0, as we are analyzing this case's probability, we have already taken p as not equal to 0. Then that means there has to be at least one non-zero element in this whole matrix p. Let's call that element here xij on the ith row and the jth column. This xij element is not equal to 0, right? I've just taken any arbitrary element. There has to be at least one non-zero element in the whole matrix P, and I've taken that to be xij without loss of generality. And if we multiply this matrix by a vector v, right? If we multiply this matrix with a vector v, the jth column of the resultant matrix, right, of the resultant vector, we are multiplying 1 by n vectors, right? So this is not the correct one. This is the correct one. The resultant vector that we get, the jth column of that is going to look like this. The jth value of the resultant vector, resultant j, is going to have a equation like this. It's going to be whatever initial vector we had. Let's say the initial vector was v1, v2 up until vn, right? Then we have v1 into x 1j plus v2 into x 2j plus up until vn into x nj, right? These x values are the values in our matrix P. So the first row jth column element is going to be x1j, and the nth row jth column is going to be xnj, right? We are assuming that xij is non-zero here. This resultant j value is equal to v1 into xij plus v2 into x2j, etc. up until vn xnj, right? Let us assume that this resultant element is 0. As we are analyzing this case right here, we can assume that the resultant is 0 here, right? So this resultant j value should be also be equal to 0. So this value is equal to 0, v1 into x1j, etc. up until vn xnj, right? Actually, this is congruent to 0 modulo 998244353 mod 998244353. And we can take the xij term on the left hand side and the remaining term on the right hand side. Let's denote this whole summation minus vi into xij as some value k, right? So we would have k on the right hand side is congruent to vi into xij, right? I have taken the vi into xij value on the left hand side, minus value, as there was a plus here, so there should be a minus value right on the left hand side, and the whole summation subtracted by vi into xij, let us call that sum k, right? As xij is not equal to 0, vi should exactly be equal to k into minus of k into inverse of xij, right? Inverse of xij modulo 998244353 mod 998244353, and we can take the inverse of xij mod 998244353 for two reasons. First of all, xi is not equal to 0, xij is not equal to 0. That is the first reason we can take its inverse, and the second reason is 998244353 is a prime number. As it is a prime number, all of the numbers that are not equal to 0 are going to have an inverse congruent to this, right? To learn this, you can look at some number theory concepts like the Fermat's last theorem and modular inverse concepts. And this vi value should exactly be equal to this value, whatever that is, right? Let us call this value as some t, right? So if vi is exactly congruent to t modulo 998244353, only then our algorithm is going to fail, right? And what is the probability of this happening? As we are selecting our v vector randomly, our vi element is also selected randomly from all of these values, uh, from 0 up until 998244353, right? Our vector v is considered a v1, v2 up until vn, and each vi is selected from 0 up until 998244353 randomly with uniform distribution. Any one of these elements between 0 and 998244353 has an equal probability of being selected. So what is the probability that t is selected out of all these? The probability is 1 by 998244353. So we have a 1 by 998244353 probability of our algorithm being wrong, right? So we can say with the 1 minus this probability, let's call this probability as p, and this p is very, very small. So we can say that with a certainty of 1 minus p, our algorithm is correct. The output that we are generating is correct, right? So, and the whole algorithm takes big of n square time. So let us code this algorithm. The code is going to be really simple, right? So in this code, we are first going to take the number of test cases. I have declared 9982453 here. Let me actually, yeah. So in the number of test cases, we are going to take the input int m, c in m. These are the inputs of the first C array, and then we are going to take the matrix A here, right? We are going taking all of the a ij values for the matrix A, right? And here we have taken the number of test cases, right? And now we are declaring a bool bad is equal to false. This bad would be turned true if p is not equal to 0, right? This bad would be true if we have declared that p is not equal to 0. And if this bad is false, then that means that if this bad remains false, then that means p is equal to 0, right? Let us ignore this for loop for right now. I'll explain what that for loop does after a while. So let us look at the algorithm for now, the Freevel's algorithm. So this is the Freevel's algorithm here. And here we have declared an answer vector in which we are going to store the entire vector which turns out. I have also declared two temporary vectors which are going to help us, v0 and v1, right? v0 is of size n and v1 is also of size n, and I also declared current 0 to basically denote which of these v vectors I am using right now, right? First of all, I have declared all of the answer values as 0 initially, and then I have declared v current I as RNG modulo n. This RNG is a very, very good random number generator, and this is the code that you can use to get this random number generator in your template as well. The standard rand function that is present in C++ does have a lot of faults, and you know, it is also biased towards some numbers rather than other numbers. This RNG does not have at least in the view of competitive programming, it does not have any kind of faults or any kind of biases. So you can use this RNG number, this RNG function, and using this RNG function we have generated a random vector which is v current I or v0i right now, right? So we have basically initialized v0 as a random vector, and then for int I, excuse me, not this one, this one, right? So for int I is equal to 0, I is less than m, we are adding answer j with ci into v current j, right? Basically we are computing the vector again and again. We are multiplying the vector v current with a so that we can get the current vector which we have to multiply with the constant c to add to our answer. So we are adding in the answer whatever value we get by multiplying the vector we have with c, right? And then to compute the next vector, we are just XORing current XOR equal to 1. We are declaring V current as 0 initially. We are setting all of its values as zeros. And then we are just multiplying the V current XOR 1 vector with A. We are multiplying 1 LL into V current XOR 1 J into A JK. We are doing a matrix multiplication here in big of n square time of a 1 by n vector into a n by n matrix. Multiplying this takes n square time, and that is what we have done here to get the V current vector, which is going to be used in the next iteration of the loop. Once we have generated all of the vectors and added those up in the answer vector, we are just going to check whether the answer vector is 0 or not. So for int I is equal to 0, I is less than I plus plus. If answer I is greater than 0, this basically says if answer I is greater than 0 for any answer I, then bad is equal to true, right? And if bad, we output no, else we output yes, right? This code is going to work with the probability of 1 by 998244353. But as you know, there are a lot of test cases, around 200, and your code might fail at some point if there are going to be a lot of test cases. If the probability is 1 by 998244353, even though it shouldn't fail, it might fail on some off chance. So if you want to increase your probability of getting a correct answer, of getting an accepted code, what you do is you just run this free-words algorithm multiple times. So I'm going to be running this algorithm number of turns time here, right, where this number of turns time I have initialized as equal to 5, right? The probability of this algorithm failing one time was 1 by 998244353, right? What is the probability of this algorithm failing 5 times in a row? Is just going to be 1 by 998244353 to the power 5, right? Which is going to be a very, very small number, right? So this will be the probability of your code failing, and the probability of success of this code is going to be 1 minus this number, right? So this is the code for characteristic polynomial evaluation, and by submitting it here, let us submit this as well and see whether it gets an accepted answer. And after submitting the code that we just built up, of course we got a correct answer, as the probability of our code failing is very, very, very small, which can be assumed to be 0. So this was the editorial for characteristic polynomial verification, which required the knowledge of free-words algorithm. Free-words algorithm is a very standard randomized algorithm, and if you want to learn more about algorithms like this one, the term that you should search for is randomized algorithms. Anyways, that was about it. Do like the video and subscribe to the channel if you want more editorials coming out. And yeah, I'll see you next time. Bye for now.